Okay, error detection and correction. So this will be the last major topic of the course. So far, we have been all about calculating the probability of error. And we basically said, if you want a low probability of error, what you got to do is you got to crank up the energy. But this, error detection and correction, is a way of trading off time against energy. So, and in fact, a very efficient way. So another thing we said, basically we said the following. ED over N naught is a key metric. So what we can do to increase EB is either crank up the energy or extend the time. Now the only way to get zero probability of error is, so if you have constant energy, then the only way to make EB go to infinity is to basically have infinite time. Error correction, very, very sophisticated error correcting codes are a way of actually achieving zero probability of error in finite time and finite energy. So, or excuse me, finite time and finite energy per bit. So there's a lot of magic, excuse me, there's a lot of very, very complicated math here. We are going to basically just scratch the surface and look at two particular kinds of error correcting codes. Those two particular kinds of error correcting codes are called block codes and convolution codes. And the basic idea will be this. Let's say I can give you a code that can, in a block of 10,000 letters, let's say, I can give you a code that can correct any 100 errors. In other words, if 1% of the bits are in error, that code can correct all of those errors. The basic idea of achieving this, so that is obviously achievable with finite energy per bit. There is some finite energy per bit you can use that leads to a bit error rate of 1%. The idea of an error correcting code is we add a bit of redundancy, and then in any block of 10,000, let's say, we can see which 100 were flipped and flip them back. And then if you think about it, in a block of 10,000, if the bit error rate is 0.01, what's the probability that significantly more than 100 will be in error? So it's it's the same kind of question as if you keep flipping a coin, about how many heads do you expect? You expect about 1/2. So in a block of 10,000, if the bit error rate is like 0.01, how many errors do you expect? About 100. And as the block length gets longer and longer and longer, that number of errors will tend to concentrate around the average. So if you can get a code that can correct exactly that fraction of errors, then you will get back to zero probability of error in finite energy per bit. So that's the basic idea. What we're going to see are very simple codes that don't really do that, but they contain the ideas for the very sophisticated error control codes that are used in modern systems. But first, I want to say a couple things. So I talk about redundancy, but what does that mean? The best way to think about this, the best way to think about error detection and correction is to think about our everyday experience. So why can we correct typos? So a typo is a kind of error in digital transmission. So I mean, when you're writing in English, there are a limited number of characters that you can send. Let's say all the uppercase characters, all the lowercase characters, a bunch of punctuation. So in total, probably 60-odd characters that we use. So there's a finite alphabet, and And basically what you're trying to do is compose messages out of that alphabet, and every so often errors happen. So why can we see and correct those typos? It's because not every sequence of characters is a valid word. And furthermore, valid words are, quote, far enough apart that errors can be corrected. So for instance, if I have the word error and I make a typo, so let's say this is like so. I mean, the only word in English, actually I'm not sure if this is 100% true, but it seems to me that the only word in English that has E blank ROR is error. So we can assume that that's probably an error. On the other hand, if, let's say, every sequence of 5 letters was a valid word, then we wouldn't be able to tell the difference between these two, or we wouldn't be able to tell which was valid between these two. Furthermore, if sufficiently many sequences of 5 letters were valid words, then this might be close to a third valid word. Let's say this is also a valid word. Then I wouldn't be able to tell the difference between these two. So I would be able to tell that an error had happened, but I wouldn't be able to tell whether it was this one or this one. So that's the fundamental idea of error correction. Basically what we want to create are sequences of letters in our alphabet that are sufficiently far apart that if an error happens, that error is still close to a code word. Okay, we will pick this up tomorrow. So once again, replacement lecture tomorrow in CSEB 3033 at 10:30.
They moved for lab 5 will be next Friday, right?
Correct. Yes.